organizer, especially Professor Han, for the very kind invitation, especially for this special opportunity occasion for Professor Dan Burns, whose work I have studied and admired since I was a student. So what I'm going to talk about is, my talk is mostly kind of like expository talk on the spectral theory of the dbar-Neumann Laplacian, so there aren't going to be much of new result. So let me first talk about the motivation. So there's this famous question by Mark Katz, which asks, can one hear the shape of a drum? So what he asked was that if you have two planar domains, if their spectrum are the same, they are isospectrum, can you say that they are isometry? Now this, of course, has been resolved. I mean, at least from perspective, this has been resolved in the early 1990s. So what I'm going to talk about actually is not this. Is kind of like several complex variable analogs of this problem. So it is about what is the spectral behavior of the dbar-Neumann Laplacian and the geometry, the interplays between these and the geometry of a complex manifold, of the underlying complex manifold. So I will try to convince you that we will be able to determine more about the geometry of the underlying manifold from the spectrum of the dbar-Neumann Laplacian than the usual Dirichlet or the Neumann Laplacian. So before I talk about the results and the methods that have used in this theory, let me first recall what is the dbar-Neumann Laplacian. So suppose I'm going to talk focus only on domains in Cn. I mean, you can talk about in complex manifolds. So suppose this is domain in Cn. Let's consider dbar operator from 0 q minus 1 q form. I mean, we can talk about pq form, but here let's it's not going to make a difference because we are working in Cn. So this would be a densely defined closed operator. Therefore, it has an adjoint, which is also densely defined and closed. So the dbar-Neumann Laplacian on 0q form is just this operator d bar and then d bar star on 0q form. And you have one before that, that will be d bar star q minus 1, d bar q minus 1. So it is a densely defined closed self-adjoint operator. Now, of course, it's non-negative as well. So, as such, the spectrum of this operator is going to be a subset on the positive real axis. So what we are interested in is how is this spectrum related to the geometry of omega. So this is how does these two interplay with each other. Now let's recall some spectral theoretic setup. Suppose I let lambda j equals to the inf of all subspace okay, before I do that, let me say that in starting this spectral theorem, one of the idea was that instead of looking at the second order differential operator, we look at the quadratic form. So we look at Q, the uv, which is defined by d bar u, d bar v. It's just the quadratic form or the Dirichlet form associated with the dbar-Neumann Laplacian. Now, the domain of this, of course, is just the domain of d bar intersect the domain of d bar star. So this operator can be defined as through the quadratic form. V is just Q uv for any u in domain of the quadratic form, and any v in the domain of. Now, this operator, as I said, is the dbar-Neumann Laplacian. Now, what is special about this dbar-Neumann Laplacian? So the domain of the dbar-Neumann Laplacian is, of course, by definition, is all the u's 0q forms. So that u is in the domain of d bar and d bar star. And d bar u is also in domain of d bar star, and d bar star u is also in domain of d bar. Now, when we so the dbar-Neumann problem asks about the to solve this equation. Now, implicitly, we assume that u must be in the domain of d bar star, and d bar u must be in the domain of d bar star. So these are boundary conditions. So these boundary conditions are what we call the dbar-Neumann boundary conditions. So, for example, if u is a 0-1 form, like this, and omega is defined by is having a smooth boundary and given by a defining function r, then u is in domain of d bar star is equivalent to uj dr dzj is 0 on the boundary. The crucial fact about these boundary sort of boundary condition is that we don't have the Hardy's inequality anymore. We have this operator, although itself it actually is just the usual Laplacian operator acting diagonally. With negative 1,4 as the coefficients, but these boundary conditions are non-coercive, so that means that you would not have a Poincare inequality. So that now, okay, coming back to the spectral theoretical setup, let's see what does this mean here. So suppose I let lambda j equals to inf of all the subspace in the domain of Q with dimension equals to j and sup of all the u in L with norm L2 norm equals to 1 of Q u. Now this is just the min-max principle. The point is that this lambda j is not necessarily eigenvalues. We don't even know whether the spectrum of these has any eigenvalue or not. That it may have no eigenvalue at all. This has not been proved yet. Okay, so but we do know the following facts. These are from spectral or abstract spectral theory for the non-negative self-adjoint operators. So first of all, lambda 1 is just the infimum of the spectrum. Now this lambda j, the limit of this lambda j is an increasing sequence, is the infimum of the essential spectrum. So this E means essential spectrum. So essential spectrum are those points in the spectrum that is either an eigenvalue of infinite multiplicity or it is an accumulation point of other points in the spectrum. Secondly, if you have lambda j is less than this infimum spectrum of the essential spectrum, then this lambda j is indeed an eigenvalue of finite multiplicity. So the a third fact is that this lambda j goes infinity if and only if that is from here the essential spectrum is empty. In this case, that is equivalent to this operator has compact resolvent. So that is that this operator is compact from L2 space, is compact. All right. So, of course, within this main theme of how does the spectrum interplay with the geometry, there are many questions to ask. But for us, At this point, we are mainly interested in the following three questions. So we want to characterize omegas, let's say in Cn, so that the spectrum, one of these is true. The first spectrum, the infimum spectrum is positive, or the infimum of the essential spectrum is positive. So this is the positivity question. The second one is the purely discrete question. So this means that the spectrum are purely discrete. So it's like the huge the Laplacian that occurs in Kantai's Professor Kantai Kim's talk. That in that case the spectrum is always discrete. So, but in this case it may not be. So this is when does this goes to infinity. So this is the spectrum is purely discrete spectrum problem. The third is, okay, if it goes to infinity, how fast can it go to infinity, and how this would relate it to the geometry. So it's, say, for example, how would you know that this goes to infinity to some power of j, of j? So for some epsilon greater than 0. So I would call this as the eigenvalue distribution problem. So I will talk about these all these three problems. Okay, so let's first talk about the positivity problem. So when does the spectrum, I mean the spectrum is always non-negative. So the question is when is the spectrum positive? Let's before we do that, let's just recall or digest it to the situation where you have the Dirichlet Laplacian. So suppose omega now is a domain in Rn, a real domain, and here, and this is the Dirichlet Laplacian. So there's the Laplacian with the Dirichlet boundary condition. So in this case, the spectrum of this Dirichlet Laplacian is positive if and only if the sup of the distance to the boundary x to the distance to the boundary for any x in omega is finite. Now let's assume in this, for this problem, let's assume that omega it has Lipschitz boundary. It could be and then this is also equivalent to the infimum of essential spectrum is positive. So all these three conditions is true. So for in particular, for any bounded domain, any bounded, when omega is a bounded domain in Rn, this of course always hold. Now, for unbounded domain, it could also hold as long as these, when you go to infinity, this would not open up to infinity. So this would also hold. So this is the case when you have the Dirichlet Laplacian. Now let's look at the case where you would have the dbar-Neumann Laplacian. So now, okay, let's assume omega is a domain in Cn now, e to n. That it turns out that the infimum of the spectrum of these on 0Q form is positive for any Q from 1 to n. On the top degree form, on n forms, this dbar-Neumann Laplacian is just the same as the Dirichlet Laplacian. So now this is equivalent to omega is pseudo-convex. So this is nothing new. This direction is just a reformulation of homogeneous L2 estimates for the dbar, because this infinite spectrum is positive, is equivalent to saying that in this case the range of dbar on 0Q forms and the range of dbar on 0Q forms are close, and the L2 cohomology, I use a tutor to denote the L2 cohomology on 0Q forms, which is just the kernel of dbar. These are dbar from L2, think of it from L2 space to the range of dbar. So this is L2 cohomology. This is trivial. So you can solve dbar for any dbar closed form. And of course, this would imply that the infimum of the essential spectrum, is a smaller set, is also positive. And it turns out that this direction also holds. But this here, in fact, for this to hold, you actually assume that this domain is a bounded domain. Otherwise, unbounded domain, the spectrum could be 0. The infimum of the spectrum could be 0. Now, for this direction to hold, you actually need to assume certain boundary condition. For example, you can that this would hold if the interior of the closure is the domain itself. So then you eliminate the situation where you have a ball, then you delete the center, where in the L2 setting, the spectrum after you delete the point would not change. It's the same as the spectrum when you of the ball itself. So in the L2. Now this, of course, this actually is just an application of some idea from shift cohomology theory. In particular, specifically, you have this classical theorem of Oka-Gardang that says that if omega is pseudo-convex, then the Dalbach homology is vanished. It's trivial. This double com. Now, we need to be careful that Dalbach homology need not to be isometry to the L2 homology. This is a problem that has been studied by Hormonger and by Ozawa and many people, but it may not be so. That this now this is, as I said, this Gardang's theorem, Oka-Gardang's theorem 2, theorem B, and this direction is also true by Laufer, and this is true without any condition. Here, for this to be true, you need to have certain boundary condition that eliminate the situation where you have a point, just delete a point. But this is true for unbounded domain as well. So this, so when you, so it turns out that one can generalize this Laufer's method to prove that one can determine whether a domain is zero-convex or not from the spectrum. So that is from the positivity of the spectrum. So now one already know that when one use the dbar-Neumann Laplacian, we can hear more about the geometry than the Dirichlet Laplacian. Dirichlet Laplacian essentially for any boundary domain is always positive. The geometry of the boundary never comes up. Now, okay, so let me also mention at this juncture that this more recent theorem of Hormonger 04, he proved that if omega is a domain in complex manifold, m-dimensional complex manifold, if the infimum of the essential spectrum, I'm rephrasing his result in spectral theoretic terms, then the Levy form of the boundary cannot have exactly q net okay, n minus q minus 1 positive eigenvalue, and and q negative eigenvalue. So the signature cannot have exactly the signature. So these are the positive number of positive, and these are number of negative eigenvalues. So this, so at least, but it seems to me that how would you how to characterize that the essential spectrum is positive on just one level of form, one degree of form? If it is from 1 to n minus 1, or is from certain number to the top degree, though this has already been done. But for just one degree, it seems to be an open problem, and there's only one direction of result. Okay, so let's look at the second problem. That is the purely discrete spectrum. So the question, is, of course, is, as I said, when is the spectrum consists of eigenvalues of finite multiplicity, and those eigenvalues goes to infinity. Now, let's again recall the situation for the Dirichlet Laplacian. So suppose omega again is a bounded domain in Rn. I mean a domain in Rn, not necessarily bounded, actually most likely unbounded. And now okay, let's assume for simplicity, the boundary is Lipschitz. One can weaken this condition. I mean, this is nothing what I talked about in the Dirichlet Laplacian case is nothing new. It's just a simple application of the Hardy's inequality. And those are classical results. So then the infimum, I mean the spectrum, the essential spectrum is empty. So that means that the spectrum is purely discrete, is equivalent to the in, this is just the in radius as x in, no, I don't want to say that. I want to, yeah. Okay, the distance to the boundary, the limit of this as x goes to infinity, when x is in omega, must be 0. So the in radius, you must look like this. So as you go to infinity, this must be closed up in order for that to have purely discrete. It could be unbounded, but it must be closed up. So again, the convexity or those kind of conditions never come up. It's just that as long as the domain close up and infinity, then that's fine. Now let's look at the come back to the dbar-Neumann Laplacian case. Now, in this case, even for a bounded domain, we do not, most likely in general genetic situation, the spectrum is not empty. The essential spectrum is not empty. Now there is a sufficient condition due to Kathleen and also by Sibony that says that let's assume here the boundary is Lipschitz, just a technicality. That says that if they introduce a property P, this in the terminology of Kathleen or B regular, in the terminology of Sibony, they are the same. Now this is a domain satisfied by a property P if if every boundary point is a subharmonic peak point. Okay, so that means that if for any P on the boundary there is this say H which is continuous up to the boundary and pre-subharmonic inside, so that H at P is 1, but on other points has modular absolute value strictly less than 1 when for any Z on omega bar minus the point closure. So this bar is closure. So let me so every boundary point is pre-subharmonic peak point, and this is equivalent to saying that for any m greater than 0, I can find a pre-subharmonic function. Let me use phi pre-subharmonic in the neighborhood U of the boundary such that phi has bounded by 1, but the complex Hertzian of these is greater than m on near the boundary. Now, so this condition, property P, implies that the boundary of the domain contains no complex variety, complex analytic variety. Now, Katalin proved that these property P, suppose omega is a pseudo-convex domain bounded, and then a property P would imply that the essential spectrum is empty for any, in this case, Q. Actually, you all, one can introduce the concept of PQ, which corresponding to the 0Q form, but here just for simplicity, let's just talk about only property P as in Katalin's case. So this is a sufficient condition. And as I said, this is stronger than the boundary is variety free. And this is also stronger than the boundary is variety free, at least in the case when n is true. This again is an observation by Katalin. So we contract this result with this result here. We already know that geometry play a role in the case of dbar-Neumann. Oh, I'm sorry. This I use box, but it should be the Dirichlet Laplacian. Okay. So when omega is convex, the situation becomes actually much simpler in the sense that we have this characterization. Omega satisfies property P is equivalent to the essential spectrum is empty. And this is also equivalent to the boundary contains, boundary is variety free. And these are all equivalent. So for convex domain, you can determine whether its boundary contains a complex variety or not by just looking at the spectrum. And as long as the spectrum is discrete, then we know that for sure that the boundary does not contain any complex analytic variety. And this was a result by Emil Strauber and myself many years ago. Now, so this, when you contract with this, the case of Dirichlet Laplacian is quite striking. That means that we actually just from the spectrum we can hear more about the geometry of the domain. Unfortunately, this kind of a clean characterization would not hold when it is pseudo-convex. So things fail when omega is only a pseudo-convex. So there is an example. Let's look at the a specific case of a domain in C2. So this is just a complete Hardox domain in C2. so zero convex, so that there's the Laplacian of this is non-negative, this subharmonic function. Now, the boundary is variety free. It contains no complex variety. One easily see that is the same as saying that these are the zero sets of the Laplacian has empty Euclidean topology. Interior in the Euclidean topology. And then the boundary it satisfies property P means that this has empty fine interior. So what it means is fine interior means that it has empty interior in the fine topology. Fine topology is a potential theoretical topology. It is a topology that you add more open sets to the Euclidean topology so that subharmonic function become continuous. We all know that subharmonic function is only semi-continuous, but if you add more open set to it, so then it becomes continuous. So this the fine topology is a finer topology than the Euclidean topology. So from here we already know that this is stronger, but this does not hold. So this in the Hurt's domain, this unlike in the convex domain, this already is not true. Now, this thing, it turns out that can be characterized in terms of Schrödinger operators. Okay, so let me just briefly talk. So this is, suppose I let this as zero phi be the Schrödinger operator with electric potential delta phi, then this thing is the same as the first eigenvalue of this t. I replace a t here. It goes to infinity as t goes to infinity. So this is in terms of t can be considered as 1 over h, the 1 over the Planck constant. So therefore, this is in terms of the semi-classical analysis of the Schrödinger operator. Now, this is the essential spectrum is empty if and only if the first eigenvalue of the Schrödinger operator with magnetic potential goes to infinity as t goes to infinity. Now, this is just this Schrödinger operator with magnetic minus I phi x squared. So this is a magnetic Schrödinger operator with this magnetic potential and this electric potential. Now this actually was an observation by Emil Strauber and myself, and then so now the fact that Cateline's property P implies that the empty it has empty essential spectrum actually follow from a famous inequality of Cattro and Bailey-Simon on the that this eigenvalue here is always the one that with magnetic potential is always greater than the one without magnetic potential. So this is usually referred as the diamagnetic magnetism in quantum mechanics. So it turns out that in this case, this is also true, and that was a result by my quiz and myself several years back. So so we can see that the theory actually has a relationship with the things that has been discussed and studied in quantum mechanics. All right, now let me talk about the last part, last question, that is about the eigenvalue distribution. So we like to see how the eigenvalue distributes when the spectrum is purely discrete. How the eigenvalue distributes. Now again, let me recall this classical while asymptotic formula. Now suppose omega is a boundary domain in Rn, and then n. Okay, these two n. Let me write this script n. Lambda is the number of eigenvalues of the Dirichlet Laplacian that are less or equal to lambda. Then, while asymptotic formula tells us that this is, as lambda goes to infinity, is this omega n. This is just the volume of the unit ball in Rn, 2 pi n, and then lambda n half times the volume of omega. So I mean that is the classical result, as they're saying that one can hear the volume of a drum from the spectrum using the Dirichlet Laplacian. Now let's consider the case in the dbar-Neumann Laplacian. Now, this theorem due to Mativier and by Nancy Standen and her collaborators, that says that if omega, let's say, is a domain Cn and is the boundary is C2 smooth, and and it satisfies a condition AQ, or in some book is ZQ, which means that the Levy form has at least Q plus 1 negative or n minus q positive eigenvalues. Now under this condition, I mean when q is 1, that is A1 is just strictly zero convex. Then you have under this condition you have the same type of asymptotic formula as in the wild asymptotic formula. So this term here 2 pi n is and you times n choose q is just because you have you can choose from the q and this term is exactly the same contribution from the Dirichlet Laplacian, but however there is also a boundary term Cz ds. Now this is just a continuous function depends on the eigenvalue of the Levy form. So in particular, when n is true and so in this case omega is strictly pseudo-convex, then the counting number is n. This would be 2 and this 2 pi 2 so times n 2 choose 1 2. Now in this case you assume you can only work on q equals to 1 and plus 1 over 96 pi square. And this is just the eigenvalue of the Levy form. In this case, you have only one eigenvalue of the Levy form. So you have this asymptotic formula. This. Now, so when you have strictly pseudo-convex, in terms of the asymptotic, the power of lambda is lambda square. So now it turns out that these actually that it goes to lambda square, or these have polynomial growth is equivalent to that the domain is finite type. So there is this theorem that we proved some time ago that says that omega, assume omega is in C2, then omega, the boundary is a pseudo-convex of finite type, say less or equals to 2m, then this counting number will be less than a constant times m plus 1. And conversely, if you have this, then the finite type of this is less than 8 m plus 1. We don't have an if and only if this direction an estimate. So therefore what we have here is that omega is of finite type if and only if this n lambda has at most polynomial growth. So what does it mean by finite type? Finite type means that when you have a variety V, and then this variety V would be the order of contact of this variety V with the boundary is at most of order 2m. So you cannot, in particular, you cannot have a variety on the boundary. Okay, so let me just indicate how this is proved. Now, in order to prove this, one of the methods is to study the spectral kernel. You can study the heat kernel, but let me just here mention this, the way to prove it using the spectral kernel. So the spectral kernel, suppose you have the eigenvalue is lambda j, the eigenvalues, and then phi j are the eigenforms, corresponding eigenforms. Then the spectral kernel E lambda ZW is just you sum all those j up, that is less or equals to lambda j phi j Z wedge phi j W. In particular, the trace of these on diagonal is just lambda j phi j z square. Now, when you are working on functions, not on forms, these, I mean, in some literature, this is also referred as the Bergmann kernel. And indeed, it's a Bergmann kernel when you work on functions, and then the trace of this E on 0, forms, which is on functions. This 0, ZZ is just all these is exactly the Bergmann kernel as in Professor Kim's talk. So studying a spectral kernel is studying Bergmann kernel is a part of the can be regarded as part of the study on the spectral kernel. So one just need to estimate this to prove this. One just need to estimate the spectral kernel. Now, on the opposite direction, that one has to assume that this has at most polynomial. This has at most polynomial growth. You need to prove its finite height, and you prove by contradiction, and you use compactly supported wavelets to construct of this is by Dobchis and also by Lemeria and Meyer. Anyway, so let me skip this, but just mention in connection a result that's related to Professor Kim's talk, and that's so suppose think about Bergmann kernel, then you have this Feldman asymptotic expansion. Rho is a special defining function that one can choose. It satisfies certain asymptotic mountain equation as in Feldman's work. Now, a theorem in the case or when omega is in C2, a theorem by Professor Burns says that if this logarithmic term vanishes to second order, then the boundary is this is locally spherical. This is in the late 1970s or early 1980s. So this, in a sense, is a theorem that if you have certain assumption on the spectral kernel, then you can determine that it is locally spherical, and indeed, then from here one can prove that if the Kähler-Einstein metric, the wave metric is a Kähler-Einstein, even without any simply connected assumption, then the domain actually is a ball. So that's kind of if one view it from spectral theoretical way, is a very interesting theory in the inverse problem. Okay, I'll stop here.